The scientific method offers scientists a basic step-by-step procedure to help ensure that their experimental results are reliable and useful. Understanding the basic principles and assumptions of the scientific method can help you conduct experiments efficiently and effectively. Formulate a question. The first requirement of the scientific method is that the scientists should study and observe the world around them and formulate a question that can be answered by the results of the experiments. Because the scientific method takes time, scientists should choose questions that interest them so that they do not get bored with the experiments they are conducting. Better questions are those that have not been asked before or that have not yet been fully answered. Develop a hypothesis. The second major premise of the scientific method is the development of a hypothesis. A hypothesis is a statement in which a scientist states what they think will happen during an experiment. For example, if a scientist is conducting an experiment or whether it is possible to live without money, the hypothesis might be: if I have no money, I will not be happy and my life will be mundane. Remember that the hypothesis is not necessarily correct. It is just a conjecture. Design the experiment. Because only those hypotheses that can be tested with a measurable experiment are valid, the third tenet of the scientific method is to design the experiment. When designing an experiment, the scientists should both consider the control group and any variables that they will be testing in the experiment. For example, if the scientist is testing whether it is possible to live happily without money, they need to define a suitable control group in which the test subjects will meet certain criteria. We must, in defining the control group, ensure that we do not unduly restrict it. This means that if the planned experiment concerns women in general, then we cannot limit women in any way in taking part in this experiment. This also applies to additional conditions. That is, the restriction in this case cannot be the place of residence, social status, etc. Draw conclusions. After conducting the experiment, a scientist draws a conclusion. Many scientists draw a conclusion by organizing and developing their results into a formal report for other scientists to review. It is imperative that the scientists include all the information they found during the experiment, whether or not it supports their thesis or overall conclusion. Developing a conclusion without bias is key to ensuring that the experiment maintains credibility. Reflect on the results. The last important principle of the scientific method involves reflecting on your results. Consider whether your results prompted you to ask further questions that might drive you to conduct another experiment. You should also reflect on your results with other scientists and determine whether your results contradict or disprove other scientists' theories. Because science offers a way to answer questions about the universe in a clear, rational way with supporting evidence, a reliable procedure is needed to obtain the best information. This procedure is commonly referred to as the scientific method and consists of the following 8 steps. Observe, ask a question, gather information, formulate a hypothesis, test the hypothesis, draw conclusions, report, and evaluate. History. The ancient Greek Aristotle was the first to propose observation and measurement as a method of gaining knowledge about the world. In subsequent centuries, thinkers refined these ideas, notably the Islamic scholar Ibn an-Haytham, who developed an early form of the scientific method, and Galileo, who emphasized the importance of testing variables in experiments. Observation. The first step of the scientific method is to observe a phenomenon, which leads to the second step, asking why a phenomenon occurs. Once you have gathered enough relevant information about a topic, you can formulate a hypothesis or conjecture. Experimentation. The hypothesis should then be tested by conducting an experiment which should show whether the conjecture is true or false. To be sure that the data obtained will be accurate, the experiment should be repeated several times, taking variables into account. Conclusion. Only after analyzing the data obtained can conclusions be drawn. Even if a conclusion is drawn, it must be reported, after which it will need to be evaluated, looking for any errors in the procedure and determining further questions to learn more about the phenomenon. Aftermath. Sometimes the continued study of a phenomenon through new observations and experiments can lead to some new theory that can be applied to other areas unrelated to the original one, but can also be changed if new evidence comes to light. A theory can become a law when it is universal and cannot be changed over time. Always, the scientific method is the accepted approach to conducting experiments. The 5 elements of the scientific method are observations, questions, hypothesis, methods, and results. Following the procedure of the scientific method not only ensures that the experiment can be repeated by other researchers, but also that the results obtained can be generally accepted. Observations and questions. Observations allow the experimenter to gather and use basic information about the principles being tested to better predict and understand the recorded outcome. The researcher or student may choose to conduct independent studies or look at similar experiments before making observations. Defining the research questions is fundamental because it defines what the purpose of conducting the experiment is. For example, a question an experiment might ask is, does the willingness of a store's customers to donate to charity depend on the day of the week? Hypothesis. A hypothesis is a prediction of an outcome that is usually expressed in a complete sentence like, the willingness to donate to charity is higher on holidays. It uses observations made before the experiment to make a reasonable claim. At the end of the experiment, the researcher will need to use the results to decide whether to accept or reject the hypothesis. It is important to ensure that the hypothesis is resistant to questioning during the experiment. Method. The scientific method section lists all the materials used in the experiment in detail, along with the exact procedures that were taken. It is important that the methods be detailed and accurate so that another researcher can repeat the experiment and expect to get similar results. It is also necessary to list the methods used because it may be useful to go back to them after the experiment to explain some of the results that occurred. Results. You must record the results of the experiment. Scientists must interpret the results obtained, giving explanations for the data collected. Most importantly, they must also draw a conclusion from the results. This conclusion must decide whether to accept or reject the hypothesis made at the beginning of the experiment. It is often useful to present the results using visual aids, such as graphs or charts, to help identify trends and dependencies. An experimental science project aims to answer systematically, that is, in an honest, step-by-step way, the questions of how something works, how things are related, or what is the effect of one thing on another. A science project should consist of 6 steps. It starts with a question to be answered, which creates a hypothesis that can be tested. Then, general background information about the project is provided, followed by methods used in the experiment. Next, experiment results must be presented in an orderly fashion, followed by a conclusion as to whether you were able to answer the question of interest. Finally, there is a discussion of the results and conclusions that places them in the context of what has already been discovered by others. All 6 parts of the project should be summarized in a brief description called an abstract. Question and reasons. Science projects begin with a question about how something works or how things are related. A hypothesis is a reasonable assumption in the form of a claim that can be tested, and such a claim makes the most sense to others when they understand the context in which the question is being asked. Therefore, you need to provide background information. Background information explains what you are trying to solve, why you choose your methods, and why your question is interesting. How was it done? Science is considered a reliable way to understand the world because it tries to provide answers that are trustworthy. Therefore, the results of experiments should be repeatable. The methods section of a science project is important because it allows other people to repeat your experiment. It can also help you and others understand later why your experiment did not work, or why, in retrospect, your question could not be tested. The methods section contains a step-by-step written recipe that you used to test your hypothesis, what you used, and how you did it. What were the results? Once your experiment is complete, you need to collect all the data and organize it in a way that is easy to understand. The results section contains the answer to your research question. Data can be organized in the form of tables and graphs. Data tables show relationships between 2 or more parameters. Graphs are also an effective way to show numerical relationships between factors or conditions in an experiment. Conclusion. The conclusion summarizes the results and provides an answer to the question that resulted from testing the hypothesis. The conclusion is a statement of the answer to the research question, but it is also often accompanied by a constructive discussion of the project. The discussion section tells you if your question has been answered, and if so, how. If your data is conclusive, the discussion gives reasons why. The discussion also places your data in the context of other knowledge that already exists, which helps the reader understand what contribution your project has made to existing knowledge. Always emphasize the effect of incremental knowledge. The scientific method defines a set of practices and conventions that will tend to produce increasingly accurate theories about how the world works. Experiments conducted according to the scientific method look for the effect of one variable on another. Isolating the dependent variable is more important because it helps explain the effect of the process on the independent variable being studied. Testing only one variable at a time allows you to analyze the results of the experiment to see how much one change affected the outcome. If you test 2 variables at once, you won't be able to tell which variable was responsible for the outcome. Variables. Variables are factors in an experiment that can change. There are 3 types of variables in a scientific experiment: independent, dependent, and controlled variables. The scientist changes the independent variable in a systematic way and measures the effect of that change on the dependent variable. The other variables are called controlled variables because the experiment is designed to keep their value constant, which is called controlling the variable. A proper experiment should only have one independent variable. Purpose of the independent variable. An experiment attempts to trace a causal relationship between two factors in a natural process, such as the effect of temperature on the rate of certain chemical reactions. To limit the measure effects to one causal relationship, it is important to choose one cause to change, the independent variable, such as temperature, and one effect to measure, the dependent variable, such as reaction rate. Allowing multiple variables to change creates a tangle of causal relationships and makes it difficult to track which change produces which effect. Confusion of variables. Imagine an experiment to test the effectiveness of artificial light on plant vegetation. If two independent variables were included in the design, for example, changing both the temperature and the amount of light each plant received, it would be impossible to tell whether the healthiest plants grew well because of the right amount of light or just because they were given a different ambient temperature. By isolating one independent variable, different results can be confidently attributed to changes in that factor. Controlling variables. Because many uncontrolled variables affect the results of an experiment, it is important to find and control all relevant variables that could affect the outcome of the experiment. When designing an experiment, think carefully about the physical and environmental factors that could change the results and develop ways to keep them constant. Study similar experiments that have been conducted by others to find variables that you may have overlooked, and study common systematic errors that can skew the results of any experiment. Human observation involves using the senses to gather information. Laboratory observations occur when a person collects and records information about an experiment in a laboratory environment. Examples of laboratory observations include noting measurements of biophysical signals or recording survey results. There are several ways to conduct laboratory observations, and the method you choose often depends on the type of experiment you are conducting. Natural and contrived. Natural observations are observations you make on subjects while they are in the real or natural environment. When conducting this type of observation, you have little control over the subjects, so collecting relevant data can be more time-consuming, but the information collected accurately reflects the subject's natural behavior. Using the natural observation method can be difficult in a laboratory setting because usually it isn't the subject's natural environment. On the other hand, contrived observations are conducted under conditions created by the observer, as in a laboratory. Contrived observations offer more control over the data collection process, but the data may not reflect real phenomena. Disguised and non-disguised. In a laboratory setting, researchers can conduct both disguised and non-disguised observations. Disguised observations are conducted when the subjects do not know they are being observed. During such observation, subjects behave more naturally, and the information gathered better reflects their true reactions. However, there is an ethical problem with this method of data collection because the subject may not want the researcher to record their private behavior. On the other hand, non-disguised observations occur when the subject knows that the observation is taking place. Ethical concerns are alleviated, but you may not get accurate and truthful information using this method. Often, prolonging the non-disguised observation causes the subjects to begin to forget that they are being observed. They begin to behave more naturally. However, this is more expensive and more troublesome. Direct and indirect. Laboratory observation may use direct or indirect methods of observation. Direct observation is looking at or studying the actual behavior or event rather than the result of the behavior or event. Indirect observation is when a researcher studies the results or consequences of an event instead of the event itself. An example of direct observation is watching people shopping in a store to see what products are selected. An example of indirect observation is analyzing the contents of store customers' waste bins to see what they were buying. Human and mechanical. In a laboratory setting, scientists can make human or mechanical observations. Human observations are conducted when an observer or researcher collects data using the eyes, ears, nose, and other senses. Mechanical observations are those conducted using mechanical devices, sensors of all kinds, often supported by advanced data processing technology. Once data is collected by these devices, it is interpreted by the researcher. Mechanical devices offer a more precise and more independent way of acquiring data. It is considered far less biased than human observations. The scientific method consists of a series of steps used by scientists to conduct experiments. A scientist's observation of the world is crucial because it leads to a scientific hypothesis. It is the first step of the scientific method and can be presented in two ways, either as natural or staged observation. In addition, there are two types of observation, qualitative and quantitative. Understanding these definitions has a major impact on planning a scientific experiment. Natural observation. When a scientist takes on the challenge to prove something using the scientific method, they must first observe something in the natural world. For example, Newton made a thesis about the existence of a force called gravity after he observed an apple fall from a tree. This would be a natural observation. Newton saw something happen in nature without any intervention on his part or on the part of anyone else. This type of observation means that the scientist will watch and wait for an event to happen during the experiment. Staged observation. If Isaac Newton came up with his theory of gravity after dropping an apple from a balcony, his observation would be characterized as staged. Many experiments begin with the scientists wondering, what if? For example, what if I dropped this apple off the balcony? What would happen? In this form of observation, the scientist creates a hypothetical theory based on thinking about something in nature, intervening in nature, and observing the event. This type of observation generally imposes the need to recreate the experiment that resulted from the observation. Quantitative observation. In the scientific method, after a scientist comes up with a theory based on observing something in nature, they begin an experiment. Once the experiment is underway, it must be observed. The scientist records observations from the experiment and collects data. One form of data collection is the quantitative method. This form of observation during an experiment uses mathematical models and relies on the scientist to collect information based on numbers, such as how many apples fell from a tree or balcony. Quantitative observation is common in physics, biology, and the life sciences. Qualitative observation. When a scientist conducts an experiment that involves observations about the quality of what happened in the experiment, it is considered a qualitative observation. An example would be the shape of apples that fell from a balcony or tree, or what happened to them when they fell. Qualitative observations can be easily dismissed in experiments that require hard mathematical data, but they are made nonetheless. Qualitative observations can be very important in experiments that require interpretation. It is not enough just to conduct scientific research. It is not enough to make a groundbreaking discovery. Research results need to be published and critiqued in a scientific forum such as a thematic conference. That is, good scientific research also requires writing a clear and understandable scientific report. The purpose of a science project report is to accurately describe the results and scientific process you used so that other people can understand your project and perhaps even replicate it themselves. For this reason, scientists and science students tend to use universal, elaborated forms of reporting. This includes the aspect of choosing a topic or question that you want to investigate, making hypotheses or your best guess as to what will happen during the experiment, listing the materials and steps you used during the experiment, describing the data you collected, and explaining the results. Of course, you will want to use a presentation or poster to showcase your project. In most cases, vivid colors, crisp images, and clear lettering will help your display stand out from the crowd. So, not only the merit of your research, but also the form in which you disseminate it is extremely important. Often the use of modern forms of media is conducive to attracting attention. Like in commerce, it is not enough to produce, you need to sell the product. And exactly the same is true in science. But to the point. Summarize your results. When it comes to writing up the results of your science project, the first step is to summarize what you discovered during the experiment. Many scientists and science students rely on visual representations of data to show the reader exactly how the experiment went. For example, you might use a table or graph to show your results. This will make your science project report look professional and easy to read. Make sure that the data is presented fairly without misrepresentation or attempts to mislead. Choose the form of data presentation so that it is easy to read and interpret. Consider using tools such as sorting, grouping, etc. if it is helpful to your audience. Address your hypothesis. You should then let the reader know whether or not the results of your experiment supported your hypothesis. It is important to remember that it is not necessarily better for your original hypothesis to fit your results, so you should never change your data to support the hypothesis. Sometimes results that do not support a hypothesis are actually better science and open the door to further research. Analyze your procedure. When describing your experimental procedure, try to comment on it, whether it was effective or not. A key part of any scientific research report is to emphasize the analytical value of the experiment. This element of a scientific project report will show the viewer or reader that you understand how to evaluate both the data and the experiment. Make suggestions. Finally, your science project report should address potential changes that could make your experiment more effective and identify areas for further research. One change that is often suggested is to increase the sample size, as a larger sample is usually better in scientific experiments. When you list areas for further investigation, try to list any questions or ideas that came up while conducting the experiment or analyzing the data. Therefore, it is a good idea to keep meticulous notes during your research so that nothing escapes you in the future. While writing up the results of a science project can seem challenging, it is also an opportunity to make your project stand out. A well-written report highlights all your hard work and can make the difference between an average science project and a truly outstanding one. Scientific experiments are based on a principle called the scientific method, which ensures that thorough tests are conducted, reliable results are collected, and reasonable conclusions are drawn. Any scientific experiment should follow the basic principles of proper investigation so that the results presented at the end are seen as reliable. Observation and hypothesis. Observing a new physical process or phenomenon is a rare event, but there are areas of science that are not fully understood. A scientist must put his observations into words in order to develop a meaningful hypothesis. Either way, the hypothesis must explain the phenomenon through a mechanism or mathematical relationship. Prediction and modeling. It is not enough to guess why something happens. The scientist must prove that his theory is correct. Predictions are made to test observations under different circumstances. The goal is to discover more about a phenomenon and prove that it exists. One way to strengthen the scientific method is to create a model. Models can be used to provide analogies for difficult, unobservable concepts. Testing and error estimation. Testing new theories is essential. Every experiment must be designed to reduce the number of variables. It is never enough to say that an experiment has been performed and supports a theory, but the methods or results are not available. Every experiment will contain a small area of error. If a theory is to be proven by mathematics, deviations from the mean are applied to the results of each calculation. Gathering and presentation of results. Scientists must record their results. Often, the original theory may be rewritten after experiments have been conducted to illustrate a new phenomena. If the experiments performed do not support any theory, they must be discarded. Each result must be double-checked, and those that clearly do not fit the pattern are further analyzed. Once the results are complied, they can be represented in the form of tables, charts, graphs, or computer graphics. Each representation must relate to the original theory. Conclusions. Once the results are available and have been presented in a meaningful way, conclusions can be drawn. A conclusion involves interpreting the results, recognizing any patterns that occur, and describing what those patterns and interpretations mean in reality. Any modeling or prediction must be transformed into a meaningful, reasoned conclusion. Conclusions from single experiments can be developed into predictions of general behavior and give inspiration regarding experiments that extend knowledge. Law formation. One of the main goals in science is to discover and prove new laws that explain how things work. When 2 or 3 models are formulated based on initial observation and a theory is successfully tested, the different models can be combined. An example of a law based on a single concept is the first law of thermodynamics. An example of a combined set of theories is the grand unification theory, a description of the universe that combines everything we already know. The essential elements of a science project are the same steps that are part of the scientific method. Ask your question. Do the research. Make your hypothesis. Conduct your experiment. Draw conclusions. Communicate the results. Since this is the method that even professional scientists use, it guarantees the most accurate results. Ask your question. A good science project answers a question about something that interests you. The first step is to identify the problem. What are you curious about? Ask a question that starts with the words how, what, when, who, what, why, or where. Try not to choose too broad a topic. Focus on only one question. In solving the problem, you should identify cause and effect in the relationship of the two elements. The answer should be something that can be measured. Do your research. A major part of your project is research. Look for answers to your problem or question. Use the internet, academic journals, and the library. Ask people who have experience in the field who can point you in the right direction. Once you have gathered your research, ask yourself the following questions to see if it is credible and worth referencing in your project. Is the research fair and unbiased? Is the research up to date? Is the source trustworthy? Does the research show original work and sources? Can others use your references if they want to study the phenomenon themselves? If you can answer these questions in the affirmative way, then you have found research that can be used in your project. Make your hypothesis. Your hypothesis determines what the outcome of your experiment will be. Now that you have completed your research, make your hypothesis. A hypothesis is an educated theory based on collected facts about the solution to your problem or question. Formulate your hypothesis like this. I think that if condition A, then result A will happen. Using an experiment, take steps to prove or disprove this statement. Your statement should directly address your original question, and your answer must be a result that is one of possible solutions. Conducting an experiment. Conduct your experiment and record your results. Your experiment tests and proves or disproves your hypothesis. Keep notes to keep track of everything you do and all the materials you use. Some experiments take place over several days. For others, you will be able to see the results immediately. Make sure your experiment is honest and not geared towards your hypothesis. Run the experiment 2 more times to make sure the results are the same each time. Draw conclusions. Analyze your data and draw conclusions. After completing the experiment, analyze the data in your notes. Your conclusion should be a written description of your answer to the problem. Write whether your hypothesis is true or false. Do not change the results to fit your hypothesis. There is nothing wrong in having a hypothesis that turns out to be false. It is a reason to experiment, and negative results are a great conclusion for you and other scientists. This often spurs new questions and new experiments. Submit your results. For your science project to be complete, you need to communicate your findings to others. Other scientists do this as well by writing reports or articles. If you attend scientific conferences, presenting your results is usually done with posters. You can easily find instructions on how to prepare this in online resources. The poster should include your question and hypothesis. The steps of the experiment can be graphically represented with photos, drawings, charts, or graphs. It is best to have your original research notes with you at the conference so that interested parties can see your progress and other materials. Present your findings graphically or in a report. If you have built a model or have some props that can be viewed or manipulated, they will make your project much more interesting. The most common structure when conducting an experiment is the scientific method. Hallmarks of the scientific method include asking a specific question, developing a hypothesis, experimenting to collect data, analyzing the data, and then evaluating whether the hypothesis is correct based on the experimental data. If the data supports the hypothesis, the results of the study may be published or shared. However, what happens if the results do not support the hypothesis? Here are possible next steps to take. Complete the write-up of what took place. Writing down the results is part of the process of evaluating an experiment. No matter what happens during the experiment, the results must be shared, whether they support or contradict the hypothesis. Evaluate all phases of the experiment: the hypothesis, the experimental phase, and the analysis phase, and disclose the results. Then identify problems that arose during the experiment and make suggestions for improvements and future courses of action. The key to developing a future course of action section is to systematically work backward to ascertain where the error may have occurred and then make adjustments to see if changes in those gaps areas might lead to different results. The record is essential to document what happened during the experiment. It becomes part of the primary literature on the topic being studied or experimented on. Make slight changes to the process, working methodically backwards, starting with a check of the analysis process. Was the analysis incorrect? Sometimes experimental data is incorrectly evaluated. This means that you need to ascertain whether the error lies in the analysis. For example, some physics experiments require mathematical calculations. If these calculations contain errors, the analysis shows data that do not match the hypothesis. Correcting the mathematical calculations is a necessary step after any experiment, especially if they affect whether the data supports the hypothesis. In addition to analysis of mathematical calculations, there may be evaluations that focus on comparisons, predictions, or making discoveries. If analyses show discrepancies, it is important to check for errors in the comparison, prediction, or discovery processes. Eliminating these errors can alleviate discrepancies between data and hypothesis. Consider whether the experiment was carried out correctly. Human error can distort experimental data, and human error can occur at the experimental stage, whether in setting up the experiment, conducting the experiment, observing it, or processing the results. Minimizing errors at the experimental stage can affect whether the results confirm the hypothesis. There may have been other variables that were not predicted or could not be measured that affected the results of the experiment. Alter the experiment. Perhaps another experiment can better test the hypothesis. There are situations in which an experiment is not the right way to test the hypothesis. Perhaps there were design problems that were not obvious in theory or on paper, but became apparent during actual application. If so, an entirely different experiment may be needed. Experiments are essentially approaches and methodologies for collecting data to test a hypothesis. In other words, experiment A uses approach or methodology A to test the hypothesis. If the results do not support the hypothesis, experiment B should be conducted using approach or methodology B. Revise the hypothesis. If several different experiments reveal that the hypothesis has not been confirmed, the hypothesis should be revised. Perhaps it is the hypothesis that needs to be changed. If so, come up with a new way to ask questions and formulate a reasonable hypothesis. Is there something wrong with the cause and effect relationship? Have relationships and correlations been assumed incorrectly? Remember that the hypothesis is a preliminary description of a phenomenon. If several repeated experiments show that the hypothesis does not work, it may be time to discard it and replace it with another, more viable one.